Hi, everyone. So thank you very much for being here. Before we start, I just wanted to, I was actually on holiday this week, basically, so I was collecting data, as you can see yesterday, and I brought you all polvorones, which is a Spanish dessert, so please help yourself at the break. This so I guess everyone has Anaconda installed. Does anyone struggle to use Anaconda, or is everyone familiar with it? Okay, if anyone has a problem, please raise your hand, and either someone around you or I'll come help you. So you have my contact details here. Please don't hesitate to reach out if there's anything I can assist you with. And I wanted us to, before we dig into the data set, I wanted us to start by asking why, why are we all here? Why are we interested in this? Why do we have this in common? And I want to tell you how I fell in love with statistics. So I was an undergraduate student that was in London many years ago, and I started taking applied statistics courses. And I fell in love with it because I realized that it's very similar to languages, which I always loved. So you have this world of data, basically, and statistics is the language that allows you to interpret that world. So either you speak it or you don't. But if you don't, there's a whole world that's going to be close to you. So it's, from an applied point of view, I think it's an amazing skill set to have. Then why should we focus on data? So as you all know, it's one of the most interesting professions at the moment. We estimate that there's going to be 200,000 people lacking in this discipline over the next couple of years. And the reason I think it's fantastic that you're all here is because obviously you're the best positioned to take advantage of this over the next 2, 3, 4 years. So there was this quotation from Eric Weinstein, who's a fellow at Oxford, and at the same time he's an MD in Peter Thiel's Capital Fund. And he said, it's better to be in an expanding world and not quite in exactly the right field than to be in a contracting world where people's worst behavior comes out. So I think here in the data world, we're in an ever-expanding universe at the moment. The expansion is not going to stop. And I know that we all have very diverse skill sets. And this is part of what makes this field so vibrant at the moment, that people with such diverse backgrounds are coming into it, learning a common language, and then doing quite interesting things with it, obviously. Then why did I take a healthcare data set for today? I think healthcare is a bit relegated, so it's underappreciated as a field. How many people here, for example, would have known that 30% of the world's data is healthcare data? So it's a huge field, and we don't give it the attention it deserves. And then I have this quotation from Scott Zeger, who set up the data program at Johns Hopkins, with his colleagues, obviously, who said the biomedical sciences have been the pillar of the healthcare system for the past century. Now in the 21st century, the healthcare system is going to have two equal pillars, the biomedical sciences and the data sciences. So it's really a fantastic field to start looking at the moment. Next, what are we going to go over today? So it's an introductory statistical data analysis tutorial. So what I try to create here is a blueprint for how you would approach a data set for the first time. So obviously, you write a report about your data set before moving forward, basically, with the analysis, with more sophisticated modeling, and obviously going towards your conclusion. So what is this first part of a report that you do when you start a data project? No matter whether it's in business or in academia, how do you start approaching it from the beginning, and what tools you use? And in an age when everyone wants to do deep learning, which is fantastic, obviously, I think sometimes it's good to also go over the basics again, because you realize that actually you forget them pretty quickly. In terms of packages that we're going to use, they're all part of Anaconda, so you shouldn't have any problems uploading them. So pandas, obviously, NumPy, Seaborn for visualization. I import matplotlib here as well, and then we're going to use StatsModels, the StatsModel package for our statistical analysis. I gave it a mat. Is everyone familiar here with pandas and Python, or should I comment the code as well here and there? Is that a yes? Is that a no? Okay, so we'll do a bit of both, and hopefully it'll be good for everyone. So matplotlib inline obviously means that your graphs are going to be shown within your code in your Jupyter notebook, and that's obviously quite a useful option. And then I gave a Seaborn option here as well. Obviously, this is entirely up to you. I wanted first to thank the people who collected this data. So all the credits are here. It was done at 4 institutes across the world, so Hungary, Switzerland, and then 2 in the US. And I wanted us to start by remembering that your data management is an integral part of your research process. So people are always very eager to jump to the modeling side, but in actually how you approach data management is a core part of the project you undertake, and there are many decisions that you need to make, and that will influence the whole subsequent analysis that you're going to do. So let's start by uploading the first data set. This is Cleveland. So here we upload with a PD read CSV function, the process Cleveland data text, header none, which means that it shouldn't interpret the first line of the file as a header. Is everyone following? Okay, perfect. So here we get an idea of the first 10 observations in this data set. We see it's a numerical tabular data set. Let's do the same with Hungary. So PD read CSV, process Hungarian data text. Here we see already that we start having problems. Then let's do the same with Switzerland. And then let's do the same with the VA dataset, which is the last one, the fourth and last one here. Now that we uploaded each dataset individually, let's concatenate them. So this is the pd.concat function. So Cleveland, Hungary, VA, and Switzerland, the names we gave them, and we concatenate them vertically. Yes, please?
Sorry, the assumption is that all the data set has been downloaded and
Yes, absolutely. So you can put it wherever you'd like, obviously, and you can grab it from there. Yes?
Which files should we download?
It's the 4 files that start with the word processed. So processed VA data, processed Switzerland data, processed Hungarian data, and processed Cleveland data, please. Sorry? Oh, you need then just manually remove it. Oh, okay. Oh, okay. Okay. So if you have a problem with the extension, just manually turn it to a TXT extension. Okay, so let's slowly progress. Now that we have the 4 data files concatenated into one large file, let's name our columns to make them more legible. So df.columns equals, and then we give the list of names for the columns that we want. So age, sex, chest pain, rest BP, cholesterol, fasting BS, rest ECG, max heart rate, exercise angina, ST depression, slope, fluoroscopy, defect, and then diagnosis. Now let's look at the concatenated and renamed data set. So we see every column is numerical. And the first questions that we ask ourselves is, what sort of study was this? So is it an observational or an experimental study, in your opinion? Yes, it's an observational study. So how do you know if it's an observational or experimental? You ask whether the explanatory variable was manipulated in the course of the experiment. And here, just by looking at the names of the columns, you can see that it was an observational experiment, which is very common in the medical world for this type of study. In terms of what a true experiment is, so only one variable needs to be manipulated. We need to have a control group, and the observations, so in this case the patients, need to be randomized, which obviously here wasn't the case. What is a quasi-experiment? Quasi-experiment is like a true experiment, but there's no random assignment, and obviously that makes a huge difference. The reason this is important is because in an observational study, the regression line only describes the data that you see. It cannot be used to describe an intervention in that experiment, basically, which would have been the case with an experimental data set. So here we're just observing, and we're describing what we're observing. The second question is it a longitudinal or a cross-sectional study in your opinion? So here it's a cross-sectional, because longitudinal means that you take the same observation, again, the same patient in this case, and you measure them over time. So the same unit of interest gets measured over time. That makes the longitudinal aspect of a study. Here it's a cross-sectional aspect. Patients were taken over time, but at one point each. And then you might want to go directly into data analysis, but I think it's so important to remember that we always start by doing background research. It's very rarely the case that you'll be the first one to look at a data set, that something will be so unique that no one else has looked at it before. So just like in any research project, in particular in academia, you start by doing a meta-study, and you look for people who've looked at the same problem as you before, and you try to learn what they've done. So here you find 3 studies, one by Detrano, one by Sundaram, and one by Sony. So in the Python notebook, you'll have the full websites. Obviously, there's no need for us to go there right now. Something else I wanted to say is that it's very important. This was done by a study. We're looking at data collected by doctors. And what you often find in data science is that people expect a lot from the domain experts, in this case, the doctors. If we were working with them right now, I think it would be much more up to us to make as many steps towards them as possible in understanding those variables, for example, in understanding what they mean medically, and how they work with them, than to expect they to teach this to us. I'm saying this because I see it quite often, and what happens is that the more interesting a domain expert is, the more interesting the data they have is, and the more you want to work with them. But the less time they're going to have to get you up to speed. So I think it's also us to the data community to start making much more inroads towards what we call domain knowledge, is basically, and domain experts in each field that you look at. So the first stage in any data study, in my opinion, is the exploratory data analysis, right? This is what's going to answer our question of what data do we have here, how does it behave like, what structure does it have, what patterns does it have. So the first point is the research, which we just mentioned. Then we organize and summarize the data. Then we look for important features and patterns. Then we look for exceptions, perhaps, and then we interpret these findings, and this is what's going to be the conclusion of our exploratory data analysis, the first part of our data report. So let's start looking at how long is this data set. So len-df gives us 920 observations, and then len-df.columns gives us 14 variables that we have in the data set. So it's not a lot of variables. The reason we start by doing this is because you had that heuristic rule, right, of how many, you should have much more observations than variables if possible. And a heuristic rule that's often given is 5 to 1. Here, we're at 70 to 1, so we're safe from that point of view, obviously. Now, what we need to do before we can start working with pandas with a data set, we need to convert all variables to numeric variables. So we saw that it's tabular numeric data. We need to tell pandas that this is what it is. So we need to take each variable and use the PD to numeric function. So dfh, we convert it pandas to numeric. We take the original series in the data frame, and what errors equals coerce does, this is an option that tells it to interpret missing values as numpy.nan values, instead of interpreting them, for example, as empty strings. So this is a very useful function because it's going to allow us to progress much faster afterwards. This is the longest block of code that we have, and we have to do it, obviously. So what I suggest you do, if you can, is to take it from the Jupyter notebook that I passed around both on the USB key, and that was part of the 2 URL addresses, if you can, and you just copy and paste if you don't feel like retyping everything right now. One more option we've been using here is for every categorical variable. So all our variables are numerical, but when they're also categorical, we also need to specify this for pandas. So we put dot as type category. So the first question is missing values, which comes up, I'm sure, in every study you undertake with data, unless it's been pre-processed before and someone has taken care of it, or unless the people who collected the data did an amazing job. but in the real world, it's often messier than that. And the first question is, why do we care so much about missing values? The problem is that almost all statistical methods that we use assume complete information about the data set that you have. So what missing data leads to is that parameter estimates will be biased, for example, statistical power of your results will weaken, and the precision of your confidence interval will be diminished as well. So this is why we spend so much time trying to deal with missing data. There are three types of missing variables. The first one is missing completely at random. The second one is missing at random, and the third one is not missing at random. So this is all expressed in terms of the probability. What is the probability of that value missing at that place? How is it linked to the rest of your data set? And that's what determines if it's missing completely at random, or missing at random, or not missing at random. If missing at random, this is important because if it's missing at random, your missing data is ignorable. The method by which it's missing, it's ignorable, and you don't need to try to find that out. If it's not missing at random, then clearly follows a pattern, and you need to spend a lot of time finding out what that pattern is before you can start trying to fill it or to deal with it. What are the standard options for dealing with missing data? So the first one is listwise deletion. So here we just remove that observation. The second one is imputation. So what you see most frequently in blogs, for example, or in tutorials is the marginal mean imputation. So you replace, for example, if in a column you have missing values, you just replace them with the mean of that column. Then you have a more sophisticated one, which is the conditional mean imputation. So here you replace them by doing a regression model based on all the other variables in your data set. So that's a more robust way of filling your missing values for a variable. And then you have more advanced options like multiple imputation, maximum likelihood, Bayesian simulation, and then hot deck imputation, which is I particularly like. Unfortunately, very few of these are supported by, for example, scikit-learn's preprocessing impute method at the moment. So I know there's a lot of work on that. Perhaps some of you know more than me there, but very few of them are well supported, like in other statistical packages. That's a place where pandas and scikit-learn, I guess, are still progressing. I put 3 links here. The second one is very good, so bu.edu, Marina Tech Report. That's an amazing report explaining what missing data represents, how you should look at it, and giving you the detail of these more advanced options for imputation. And then, of course, there's Paul. I took here a quotation from Paul Allison, who says that the only really good solution to missing data is to not have any. There's no, unfortunately, there's nothing you can do. By definition, it's going to weaken your statistical methods, but you have to deal with it.
But if the column is the most important than
Then it was a poorly done study, and you can't use that data. I'll be honest. And we'll actually see something here. So how do you check for the missing data? Obviously, we use the pandas isNull function. So that's a function that looks for missing values, for the numpy nan values. And then we give it value counts so that we see if there's any true or false, how many there are. dfh isNull value counts, and we see that for age, it's false everywhere. So there's no missing values for this variable in our data set. Then I do this for every variable. I mean, you have to. dfsex isNull value counts. Again, we have no missing variables. This is perfect. Then I'm looking at how many men you have, but we'll come back to this later. And in this section, in short, I'm just looking at every variable, every column in the data set, and I'm trying to figure out if there are missing values, and if there are, how many there are. So rest BP, for example, blood pressure at rest, you see that here you have true, so 59 variables are missing, 59 observations, sorry, are missing for this variable. But what you want to also know, in this case, when you start finding missing values, is what do they represent versus your data set, for example. So here, if you do df-resbp isNull, so you find all the missing values, then you count them, and then you divide them by the total length of your data set, you get the percentages of missing values. So here we see that we have 6.4% missing values for this variable. df cholesterol, we have a bit more, we have 30. df fasting BS, we have 90. And what I wanted to point out here is that the standard value counts method function ignores missing values. So see, for example, if we just believe this, if we didn't give it the drop now equals true a parameter, you would tell us that there's here we have around 830 values when we know that we have 920. So it just didn't show them to us basically. That's why it's very important to start dealing with the missing values before you start analyzing your data set. Here we have very few. Max heart rate, 55 missing. Exercise angina, 55 missing as well. And here is where it gets really problematic. So you have DF slope, you have 309 missing. So that's 30% missing, 33%. Fluoroscopy, you have 309 missing. And defect, you have almost half missing, so 47%. So that's where your question comes in. What do you do when you have a variable and half of your values are missing? So right now, at this stage of our data analysis, we record all these things, and we save them for later, basically. So it's important to record where do you find missing values, what percentage you represent it out of your total number of observations, and then if you decided to do anything about it already, or if you're going to keep them for later and deal with them in the missing data part of your report, which is a whole chapter by itself in cases like this. So what I decided to do here, for the purpose of the tutorial, we don't have the time to get into this fully, but where we have 33% to 47% of missing values, I doubt you'll be able to get much useful information out of that, or that you'll be able to correct it without introducing your own biases in it. So I reduced the data set. Fluoroscopy is a more invasive exam, and that's why it wasn't recorded. Probably many times it wasn't done. And in this context, you can't sort of fill it in, at least not quickly. So that we can progress with our data set, I decided to eliminate 3 variables already, the ones where you have more than 33% of missing values. And then here, what I did for the one that REST ECG, which has only 2% of missing values, I replaced it with the mode. So filna, dfred, I took the mode of that variable. You need to specify ilog0 because you can have several modes. That's something linked to how pandas represents the mode. And then in place true. So here overall, we replaced 1 because we only had 2% of missing values. We're comfortable that we're not introducing heavy biases into our sample by replacing only 2% with the mode of the series. But we couldn't do anything about the ones where we have 33 to 47% of missing values. So what I wanted to see then, and this is literally how I started working the data set from the beginning. So I wanted to see if I try to build a clean data frame where I just take the parts of each variable that are not null, that are not missing, do I still have enough observations to get an idea of this data set about? So sometimes it's horrible, right? Like sometimes you try to select only the variables, the observations where you don't have any missing data, and you end up with 0 lines in your data frame. Here, however, you see I took all the variables where we had missing data. So dfred REST-BP not null, and dfred cholesterol not null, and dfred fasting BS not null, and df max heart rate not null, df exercise angina not null, and df ST depression not null. And luckily, we realized that we still have 741 observations remaining. So clearly there is overlap between the different variables, but for this we really need to start to dig into it, to see was there among the 4 centers we took, remember we uploaded 4 files, was one of them sloppier than the other ones? Why does there seem to be so much overlap between these different values? And that's a whole chapter by itself in terms of missing data. Here, so we can progress, what I decided that keeping 85% of our observations is enough for our initial data exploration. So we have 741 clean observations, no missing data. Now we look at the whole data frame just to check. df clean is null any, and we see that for every variable it's false. So those are 741 solid observations. I mentioned here, I wanted to explain, so the Jupyter notebook that I uploaded has a lot of explanations in it. And that's because when I was going back years now, when I was migrating from R to pandas, for example, you find a lot of amazing tutorials, and people are presenting them really well. But then when you take their notebooks and you want to do it by yourself, you spend more time trying to understand why they did something than how they did it. So I wanted to avoid that, so I put a lot of explanations across the notebook. So now that we cleaned the data, we have a data set of 741 observations that we can work with, and we can finally move on to univariate analysis. Is everyone familiar with univariate analysis already? So univariate, because you start by looking at each variable one at a time. So that's the first thing, is to get a better idea of each variable. How is it distributed? What is it? What does it tell you about the observations in your data set? This is part of descriptive statistics. And here you have the very important notions of parameters and statistics. So parameter is calculated when you have the whole population, which you almost never do. And the statistic is something that you calculate from your sample about your parameter. So these are two terms that you often come across. And in studying samples, we also make the assumption that the central limit theorem holds. So if you draw enough random samples from your population and each sample is large enough, the distribution of the statistics that you get from your samples will follow the normal distribution, will be normally distributed. And the normal curve goes back to the beginning of the 18th century, Abraham de Moivre, but it's only in the late 19th century that someone had the idea of starting to use it as an ideal histogram. So what do you look for at this level, in terms of descriptive statistics? You look for measures of center, measures of spread, and measures of modality. So what are the measures of center, to begin with this? You have three of them. So there's the mean, there's the median, and then there's the mode. Then you look for symmetry or skewness, and this is at the shape of your distribution, of your frequency distribution. It could be unimodal, it could be bimodal, sometimes it's uniform. And how you look at it is going to be determined by what type of variables you're working with, as we're going to see the rules right here. So we analyze the shape visually by looking at the frequency histogram. Then we check for measures of center, such as mean and median. And then we check for the spread. So the spread is expressed by the standard deviation, right? What is the standard deviation? It's a measure that tells you how far your observations are in average from their mean. In a normal distribution, 68% are within one standard deviation, and 95% are within two standard deviations of your mean. So that's why you get a nice symmetric bell shape. For quantitative variables, you check the shape, the center, and the spread, and you use a histogram to visualize them. For categorical variables, you can only check the mode because they don't have a mean, right? And that has a lot of influence afterwards for how we can visualize them. And you look at the mode, and then you visualize them with a bar chart or a frequency distribution. So, to recap the rules for visualizing data, if you visualize one variable at a time, and it is categorical, you use a bar chart. This is SNS's count plot function, as we'll see. If it is quantitative, we can combine a kernel density estimate and a histogram with the SNS displot function, as we'll draw it right now as well. And then, for visualizing two variables, we'll get to that in the bivariate analysis section. Let's start with gender, right? Let's get an idea of what these 741 observations we have, how are they distributed by gender? So we use because it's a categorical variable, as we said, we use the SNS count plot function. So here you see on the x-axis, you give it the explanatory variable, the variable of interest, sex, and then you give it the data set. Data equals df clean, so this is the data set you're taking that variable from. We give it a title with the PLT subtitle function. And here we see that there is a class imbalance. So you take note of this. So there's way more women in the study than there are men. Will this have implications? This is where we need to start thinking about it. What about the diagnosis? So this is the response variable. Obviously, we're doing this whole thing to look at the response variable and to try to predict it. So how does it look? We have 0, 1, 2, 3, and 4. So we see that almost half of cases are 0. So they don't have a pathology. And then 1, 2, 3, and 4 are different pathologies. And we see that 27% of the population is in the first one, and then 10% in 2 and 3, and only 2% in the fourth one. What sort equals false tells your value counts function is to not sort the values by the most frequent one, so to leave them as they appear in the data set, in the order in which they appear in the data set. Normalize equals true is an attribute that tells value counts to return to you the percentages instead of the absolute counts. Then we visualize the diagnosis with the count plot. It's a categorical variable, as we said, as well. And here we see that almost half are in the no pathology. And then we have 1, 2, 3, and 4 showing different medical conditions. Let's look at age now. So age is different, right? Because age is quantitative. So what do you apply here? Well, here you're interested, obviously, in the mean, the standard deviation, as we said, the minimum, the maximum. And for this, we have the describe function, which is perfect. So we take the column, df clean age, describe. We see that we have all the 741 observations we expected. The mean is 53 years old. The standard deviation for this is 9.4. The youngest patient in the cohort was 28 years old. The oldest was 77 years old. So the SNS displot combines the matplotlib hist function with the SNS KDE plot function. We draw age as a quantitative variable, SNS displot, df clean age, and then distribution of age, and here we see how it's distributed. So here we have the age, and here we have the distribution of patients in the study by age. And this, what shape does this have? Sorry? It looks like a bell curve, but it's also unimodal, basically. So it has one mode. Sometimes if we looked at it and it had two modes, that would be something we'd take note of as well. But it's unimodal. It's not a perfect bell curve, but it's not too distorted either. We look, here I was looking at the columns. So again, here we follow literally how I approached it in preparing this. Then we look at df clean max heart rate, another quantitative variable. So this is the maximal heart rate recorded for each patient. We have the full count again, mean 138, standard deviation 25. Minimum is 60, and maximum is 202. So here we see that we have a wide range, actually. We plot it as well with the displot function, same for age. And we get this shape, this figure. And this is a plot that I really like, the swarm plot, which is given by Seaborn. So here I plotted the diagnosis, which we looked at before, by counts. So here you have the diagnosis, and these lines show you about how many observations were in each. The swarm plot is a very useful graph that Seaborn offers. Now that we looked at a couple of variables, we're not going to do it for each variable, but you would be expected absolutely to do it for each variable in your data set. Looked at each one of them individually, based on whether it's quantitative or categorical, and then possibly also visualize it for yourself and for the other people you work with. Now we can move on to visualizing two variables at a time. So what are the rules for two variables? Are you all familiar with this? So if your explanatory variable is categorical and your response one is quantitative, you do a bivariate bar graph and you use the SNS factor plot for this. If you have two quantitative variables, you use a scatter plot, and this is given to you by the Seaborn reg plot function. And then if you have, what do you do if you have categorical to categorical? How do you guys plot that usually? You could, but normally you'd use that also for a quantitative response variable on the y-axis. The problem why those figures are not very meaningful for categorical variables is that there's no mean, basically. So that's why no matter what shape you look at, rectangles, no matter how you express them, the fact that you don't have a mean to your categorical variable, if you want to put it on the y-axis, means that it doesn't amount to something very meaningful. Oh, so you do 2 by 2, basically. Yes, absolutely. That's one way of doing it. That's a way of manually going around it. Absolutely. So we look at sex versus age. So SNS factor plot. Here we give it the x variable. We give it a y variable. Kind equals bar. And then we specify the data set df clean. So we see that the age is almost the same, identical between men and women. There's no difference here. Yes? No, I don't think that's the standard deviation. Yes? Can you repeat the question? Oh, yes. So so you're asking if the small bar here on top is a standard deviation. I'm not sure, actually. we can look into it. So here we take something else. We take gender versus blood pressure at rest. So here we have a qualitative categorical variable on the x-axis, and then we have a quantitative on the y-axis, right? So let's look at it. SNS factor plot, x equals x, y equals rest BP, data equals df clean, kind equals bar. And here we see that, again, there's actually no difference. So it seems that gender doesn't influence too many of your other variables in the data set. It seems that men and women are pretty similar in how they record these variables. What about two quantitative variables now? What would you use for that? So we said you're going to use the regplot function from Seaborn. And here we have quantitative on the x-axis and quantitative on the y-axis. So SNS regplot, x equals h, y equals cholesterol. Let's check, as you get older, does your cholesterol level, your serum cholesterol level go up or not? So that's what I wanted to look at. We plot it, and here we have age, and we have cholesterol. And if anything, it looks like it's decreasing, right? Which is really weird, but this is what the data tells you. I would have expected a line that slightly goes up. It's not the case here. Those are your data points, yes, and this is your, so what regplot does, it plots your variables basically, your value, your data points, based on what you have on the x-axis and what you have on the y-axis. And the line in the middle is the regression line. So the farther a point is from that regression line, the more likely it is that either that point or its errors basically are not explained by your model. Oh, you're looking at that. Absolutely, we can remove them basically. No, you're right, and that's why we do this. I thought you're looking for extreme outliers in the graph. Okay, absolutely. So in terms of, to come back to the categorical variables, how would you be able to get a better idea of how two categorical variables interact, since you can't really plot them the way you plot the other types of variables that we just mentioned? And one thing is to group your data set. So we do the df clean group by gender here. Then I take the diagnosis column, and then I take the value counts and I divide it by the length of the full data frame so that it gives me the percentage. So here we have men on top, 0. We have women here. And then we have the percentage of the data set that falls in each diagnosis by gender. So this is one way of manually getting around the fact that you can't plot them in another way. If you want to get a better idea of how two categorical variables interact, grouping by one of them, and then taking the value counts or the percentages like here of the other is one way of trying to get around it and getting a better idea of how your data set is distributed versus those two categorical variables. Then you have the box plot function, so SNS box plot, cholesterol on the y-axis, gender on the y-axis, data equals df clean. So here we have the extreme outliers. And again, this is one way of getting around the fact that you want to measure cholesterol by sex. It's another way of visualizing, basically. We would have put cholesterol on the y-axis like we did before. Here we decided to draw the box plots, which is a common statistical figure. And perhaps one of the most important functions that Pandas offers you is that you can group by your whole data frame by a variable of interest, here diagnosis, that's what we're trying to predict for, and you can describe it. And what describe does is going to take away your categorical variables. Again, they have no mean. You cannot calculate measures like the mean for them. But it's going to take all the quantitative ones, and it's going to give you the key statistics for all of them by the variable that interests you the most. So here is diagnosis. We have all the categories, 0, 1, 2, 3, 4. And then here we have age, we have cholesterol, we have max heart rate, we have rest BP, and we have ST depression. And we have the mean, we have the minimum, the maximum, we have the quartile splits, and the count that falls in each of them. So this is a way of getting an overall overview of your whole data set at once. Now, before starting, until now, we just observed the data set, we described it, we didn't, beyond the initial data management, we didn't manipulate the data set. So the idea is, once you start manipulating the data set, manipulating your variables, it's good to make a copy. So dfclean copy equals dfclean.copy. So we don't work with the original data set that we cleaned, we keep that aside. And from now on, we work with a copy of the data set. And now we move to inferential statistics. So until now, it was descriptive statistics. Now we finally get into the inferential statistics part. Anyone, why is it called inferential statistics here? Because you're using your sample to infer statistics parameters about the whole population, right? Absolutely. And what are the steps that you always take at this level in your data, like in your process? What do you start with? Exactly. So you start by making hypotheses based on what interests you, and every time you have the null hypothesis, right? And then you have H1, the alternative hypothesis, and you try to see if your data from your sample backs your alternative hypothesis or not. So the process, you define the null hypothesis and the alternate hypothesis. You choose the sample, which here we've already done. We analyze the evidence based on the statistical test that we're going to be using, and then at the end we interpret the results. Typical null hypothesis is that there is no relationship. The two variables you're looking at are independent. Typical alternative hypothesis, there is a statistically significant relationship between your two variables. Now, the bivariate statistical tools that we use. So when we test two variables, one against the other, what do we use? There's three main ones, right? So there's ANOVA, there's chi-square, and then there's the correlation coefficient. Anyone knows the difference? They all make assumptions. That's the thing about statistical tools. Each one makes its own assumptions, and the way you're going to be using them comes partly from the data you have and partly from your knowledge of these assumptions. You're absolutely right, though, in some of the differences you make, but it's the type of variable, again, that's going to determine which one of these three tools we're going to be using to test for independence or not. So what are the key here? The key idea is that a result is statistically significant if it is unlikely to be the result of chance. So we take the problem a bit the other way around because this is the best we have. So you state a null hypothesis. So you suspect there's a relationship between two variables, but you first state a null hypothesis and you say, look, there's no relationship. And then you look at what the data tells you. And the way you're accepting your alternative hypothesis, your H1, is that you're saying, how unlikely would it be to see this data, to see the statistics in my sample, if the null hypothesis was true? That's the underlying logical reasoning behind all three tests. Then we're going to check the p-value when we look at the first ANOVA table. We're going to check the F statistic as well. And then I mentioned here again that before using any of this analysis, you need to use the drop now function, so to drop all your null values, because they all assume perfect information. Here we cleaned the data set. We kept only 741 observations of 920, but you wouldn't be able to use these functions with null values. So let's test the idea that age and diagnosis are not related, right? So as I was saying, it's the type of variables that you have that will determine which one of these three tests you're going to be using. So if you have an explanatory categorical, a categorical explanatory variable and a quantitative response variable, you use an ANOVA table. If you have an explanatory categorical variable and then a response categorical variable, you use the chi-square test. So the chi-square test, as you were saying, actually implies a different distribution. And what it does, it implies that your options, your outcome options, amount to 1. So that the whole probability universe from 0 to 1 is covered by the choices you have, the categories you have. That's why it's used for categorical data. Then if you have an explanatory quantitative variable and the response categorical variable, what you need to do is you need to bin your explanatory quantitative variable, and then you need to use the same thing as the previous line, the chi-square test. So categorical, categorical, chi-square test. And the last one, explanatory quantitative variable and response quantitative variable, you use a Pearson correlation, which is perhaps the most straightforward one. So here, as you saw in the data set, what our response variable is the diagnosis, right? 0, 1, 2, 3, 4. But what we're doing here with this stats model is that we're putting the age as the response variable. And I wanted to ask you, is this completely wrong to you? Like, we're turning the problem on its head, right? Is this something you're allowed to do or not? So we are being a bit naughty, but we're not overly naughty in the sense that it's something that you are allowed to do. So you're allowed to invert your x and y in your analysis. And this is why you can never imply causation, because the direction, you can change the direction between the two variables. What you have is correlation, but you never can prove causation with these types of methods. So that's why actually we can very well try to use diagnosis to predict age based on our data set. And this is also the reason why we won't be able to say this causes this, but only that they are associated in one way or another. So here we have the SMF-OLS model. So SMF.OLS, and then we give the formula for the model in parentheses. Formula equals here age, response variable, then the tilde, and then diagnosis. And the C tells StatsModels that this is a categorical variable. We specify the data set, data equals df clean copy, and then we fit it. And then we print the summary. Oh, it's back? Perfect. OK. So this is what our first ANOVA table looks like. So you get the OLS regression results, right? And then we look at the variable that we use as an explanatory variable, so the C diagnosis. And we have the T1, T2, T3, and T4, with the T0 becoming the baseline. And the most important parts for us here are the coefficients that our linear regression model comes up with, and then the P statistic associated with those coefficients. So what we see is that we have an intercept of 50, so that's where we'd start with the explanatory variable being 0, and then 50 being an age here, and then how does it progress? By type of diagnosis that you have, basically, by type of categorical explanatory variable. So from the p-value, we see that they are significant. So you'd be able to say that these explanatory variables are significant in helping you determine people's age. And here we have the assumption that the model makes. Standard errors assume that the covariance matrix of the errors is correctly specified every time. Before we go into the first post hoc test, is it OK if we take a 5-10 minute break now? We're almost halfway through, basically. And from now on, it's going to be linear regression and logistic regression. OK, I'll be here. Please tell me if something's not clear. Come see me, and I'm perfectly available, obviously. So we looked at the first ANOVA table, right? And what do we see? We see, among others, right? We see the R² statistic. We see an F statistics right here. We see the p-value associated with the F statistic. So before we even move on, let's discuss this. What is the, who can give me a definition of what the F value stands for? How is it calculated, basically? What is it? Okay, so it's the variation among sample means divided by the variation within samples. Why is this important? Is because we're trying to show that the groups we're looking at are not independent, right? So that's why you look at the variation among sample means, basically, so between samples, divided by the variation within each sample, which you may call a more natural variation. This is the ANOVA F test. This is what it gives you, and this follows a certain statistical distribution, which you can read by taking the 28.42 F statistic, and it's that number that also is going to be linked to the p-value that's right under it. What matters the most to us here is obviously the fact that the p-value shows that it's highly significant, right? I mean, we have 5.56 e to the power of minus 22, so we move 21 zeros to the left right now in the number. So we're way below 0.05, which is the usual limit we take, which, by the way, that's a historical practice, basically. There's a lot of the debate right now about why is it 0.05, why would you reject a study if you're at 0.06, how much data wrangling, let's say, goes into making sure your p-value is going to be below 0.05. So there's no solid basis beyond that. It's a convention that we've adopted a long time ago already, and that we're still applying. So we have our F statistic here, and we have our p-value here. This is the key in the ANOVA table. And then we see that for every level of our explanatory variable, in this case diagnosis, it gives us a coefficient and then an associated p-value, which tells us if that is significant or not. And we have a confidence interval for it as well. So we're 95% confident that the value for diagnostic group 1, for example, is going to be between 1.134 and 4.153. While the average it gives us here is 2.64. What happens now is that our explanatory variable has more than 2 levels, right? So whenever your explanatory categorical variable has more than 2 levels, you need to also perform post hoc statistical tests. Why is that? Because you want to better understand the relationship between your response and your categorical variable, and you want to make sure that what you know now is that your groups are different, so you rejected your null hypothesis based on your p-value, but you don't know how they are different. Maybe because you have several groups, several levels of your categorical variable. Maybe, for example, diagnostic group 3 and 4 are actually the same. So for them, the null hypothesis holds. They are not different. Maybe you rejected it because your group 1 is so different from your group 4 that's what's causing your statistical power in the test. But then you want to look at every groups. You want to associate each 2 groups one against each other to make sure that you're not rejecting the null hypothesis when it's actually true in part of your analysis. Yes, please. Yes, because what happens is that we specified it's a categorical variable for StatsModels, so it immediately decided that the first one, 0, is your base variable. So it holds that one. You'd read this by saying, compared to T0, T1 has a coefficient of 2.64, basically, and you'd multiply that by your observation. So it sets, for categorical variables, you're typically looking at n-1 when you're analyzing them. So here, something we can do already is to look at the means of the different groups. So let's see. Let's take each diagnostic group, and let's look at what the mean age for that group is. So we have 0, it's 50, 1 is 52, 2 is 58, 4 is 59. Then we can look at the standard deviation as well to see if those differences in means are large enough. This is very heuristic. We see 9, 8, 7. We can't really make up our mind here. We can't really decide something. So there are several tests that allow you to take a much better approach here. One is the Tukey HSD test. Another one is the Holm T test. And then another one is the least significant difference. And then you have Schaffer and a couple of other ones as well. The code for a Tukey HSD test is this one. So we create an object, Tukey1, multi.multi-comparison. We take the 2 series within the data frame that we're trying to compare, df clean copy age and df clean copy diagnosis. Then we create the res1 as an object, and then we take its summary, which gives you actually the Tukey HSD summary statistics itself. So this is the code here. And what we see here is that it takes every 2 diagnostic groups, and then it compares them in terms of age to try to see if they're significant. So that's what we said. We know that we accepted that diagnostic group can help us predict age, but then we don't know why. Is it because groups 0 and 1, for example, are very different, but groups 3 and 4 are the same? This is what this type of post hoc statistical test does for you. So here we see we have group 1, we have group 2, so it compares them 2 at a time, right? Pairwise comparison. It gives you their mean difference. It gives you the lower and upper bounds. And then in the reject column, it tells you if your alternative hypothesis is true or not, basically. So if you should reject your null hypothesis or not. And what we see, for example, is that for the last 3 ones, so groups 2 versus 3, group 2 versus 4, and group 3 versus 4 by age, here we cannot reject the null hypothesis, actually. So we wrongly rejected the null hypothesis before for the whole study as a whole. But actually, if you drill down into the detail, you realize that here we cannot. And whenever you cannot reject your null hypothesis, you also see that in your lower and upper bound for your coefficient includes 0, basically. So you're always going to go from minus to plus something here. And that's why it's possible that it's 0, that actually there's no difference between them. So let's test another hypothesis now. So let's decide that we want to see if the presence of chest pain is indicative of the diagnostic state of someone. I mean, you'd expect that chest pain would contribute to predicting if they're healthy or if they have a heart pathology, right? So our alternative hypothesis here is the presence of chest pain and diagnosis are not independent. Here I put an aside about feature engineering because it's the first time that we manipulate the feature itself. Here it's going to be the response variable. We're going to recode it, actually. We're going to turn it a multi-level variable into a binary one. But it's a discussion of feature engineering and how important it actually is. But this is something that obviously would come into the middle of your study, not in your first initial data exploratory part. I also put some links here to some very good articles on this. So the first one explains this really well, and the second one, Trevor Stevens, applies it in the case of the Titanic, the Kaggle Titanic dataset, which many of you are familiar with, I imagine. And that's where you see just how these engineered features regularly end up actually becoming the most important features in your models. What we're doing here is we're recoding our response variable. So we have 4 levels now, right? Of 0, 1, 2, 3, 4. Ultimately, what we're interested in is just, is the patient healthy or not? Like, do they have a heart pathology or not? So we're going to turn it into a binary variable. We create a dictionary, and then we map that dictionary onto our series. We see that the result is that 384 patients had a pathology, and then 357 didn't. And now we're looking at 2 categorical variables, right? You have diagnosis, which is binary, and you have chest pain, which has 4 levels, I believe. Yes, 4 levels. So what do you do here? It's here you can't use an ANOVA table again. So it's here that you start using the chi-square, which is suitable for categorical to categorical. What you do is that you first create a contingency table, and you always put the response variable first. So the response variable is vertical, and then the explanatory one is horizontal. So here we have diagnosis 0, 1, and we have chest pain 1, 2, 3, 4. And the PD crosstab function allows us, we give it the 2 series from our data frame, and it allows us to show how many values, how many observations fall into each group. So healthy and chest pain 1, healthy and chest pain 2, etc. basically. Then what I'm doing afterwards in the column percentages, I'm simply converting this into a percentage basically per column. So the 23 and 15, or 128 and 22, this gives you a more readable version of the same cross table. And then you move on to the chi-square test. So what the chi-square test does, it actually recreates a column, a table like this. It's like the one you have on top there. And it creates it with the assumption that the 2 variables are independent. So it looks at how many observations should fall into every of the 8 boxes we have there, let's say, if the 2 variables were independent. Then it looks at what you actually have in our data set. And then, as usual, with statistical tests at this level, it decides how likely would we be to see what we see in the data set versus what we would have if the two variables were completely independent. So print, this is simply for us for readability. We say print the chi-square value, the p-value, and the expected counts. And then we create the object CS1, scipy.stats, chi2, so chi-squared contingency, and we give it the table that we created above, here. And then it gives us a chi-square value, which is the result of the chi-square distribution. And then it gives us the associated p-value to tell if it's significant or not. So as you see, we're way below 0.05. So we can consider that it's significant. And here we have the expected counts in parentheses, actually, which is what would have been expected if the two variables were independent. Here, you'd have the same problem, right? I mean, we have an explanatory variable with multiple categories. So again, right now we rejected the null hypothesis, but we don't know exactly why. We don't know how those different groups of the explanatory variable are behaving. So you'd perform something very similar to what we did before, but here it's called the Bonferroni adjustment. So basically, you adjust your p-value by the number of pairwise comparisons that you'd be doing between your categorical and your response variable. So you'd significantly diminish your p-value, actually. And then you'd perform those pairwise comparisons per group of explanatory variable. And then you look which two groups, based on your adjusted p-value, you can reject the null hypothesis versus you cannot. Just as we did before, but it's a different type of method because we're dealing with a chi-square test and categorical variables here. Let's look at our columns, basically, to see if there's something else we'd like to check. So here I'm looking at whether gender is associated with the diagnosis. Are women more likely or less likely, for example, than men to have a heart pathology or not in this data set? We create the PD crosstab as before. We look at the column percentages as before, and then we run the chi-square test. And the chi-square test, once more, it has a value of 65, which you can read using the distribution. And then it has a very low p-value. So arguably, gender is also significant in predicting the diagnostic group of someone. Something that I wanted us to touch upon here is moderators. So what are moderators? A moderator is any third variable that significantly affects the direction or the strength of the relationship you found, basically. So this is one of the main reasons why you can only talk about correlation and not causation, because sometimes two variables are very closely associated. A very common example that's given is basically how large a fire is versus how many firefighters are there. So these two are very correlated with each other, but you cannot deduct a causation between them, right? It would be wrong to say that more firefighters cause a bigger fire, which is what your data would be telling you, basically. Obviously, this is where a moderator comes in. That's what the third variable is. You call them moderator variables, lurking variables, or confounding variables. All these terms are used in the literature. And what that does, in our case, it would be the seriousness of the fire. So it's the seriousness of the fire that determines how big the fire is and how many firefighters are there. Although the two seem correlated at first, and you'd be keen but wrong to deduce a causation. So how do you check for a moderator? How do you check whether a third variable is a moderator in the relationship that you just found? What you need to do is you need to take your data set and you need to split it by values of that third variable. And you need to see if your statistically significant relationship between your explanatory and your response variable holds for each level of the third variable. If it holds for each level, it means that it's statistically significant in the presence of the third variable and that is not a moderating variable. If, however, you find that it doesn't, that doesn't hold for some level, then that third variable moderates the relationship between your explanatory and your response variable in this case. So here it's very simple because we're wondering whether gender is a moderator in the statistically significant relationship that we just found between chest pain and diagnostic group. So what we need to do is we need to take our data frame, and then we need to divide it by gender. As we said, there's two groups in our hypothetical moderator variable, right? There's 0, which is men, and then there's 1, which is women. And again, we see that there's much more women in the study than men. And what we need to do now is that we need to run a chi-square test for each of the 2 new data frames that we created. So we need to see if chest pain is related with diagnostic group for both men and women. And if it is, we can say that gender is not a moderator variable in this relationship. If it's not, then gender is. We have a relationship that is significant for women, but not for men, or vice versa. So we run the chi-square tests as we did before. And here, for example, the first one we started with is men. So we see that for men, we have a chi-square statistic of 39 and then a very low associated p-value. So again, we can say that it's, the relationship holds between chest pain and diagnostic group for men. Now, does it hold for women as well? Now we're taking our data frame for women, df clean copy women diagnosis binary and df clean copy women chest pain. And let's see if it holds for women as well. Here we end up with a much larger chi-square value, and then a very small p-value as well, way smaller than 0.05. So we can say that the relationship is significant for women as well. So we can conclude that gender is not a moderator variable. But that's how you test for a moderator variable. You need to divide your data set by levels of that hypothetical moderator variable, and you need to see if the relationship that is statistically significant that you found holds for each level of that third variable. Yes, please. Yes.
So is there like a ratio that you should target to say that both significant?
Yes, so that's what I was trying to say before, that we, as a historical practice in statistics, we use 0.05 at the thresholds level. So if your p-value is smaller than 0.05, you can say that it's statistically significant.
No, what I mean is the difference in the p-value.
In that case, no, you wouldn't. Like, for example, when values are below 0.001, you don't even record them. You just say p-value below 0.001. That's just a value that tells you if your F statistic or chi-square statistic in this case is significant or not for the type of data that you're observing, basically.
The order of nothing here, like the one is -3, the other one is -8, so then it's different. That doesn't, you're saying it doesn't matter at all.
You mean the chi-square statistic?
The p-value. So the women is much more.
No, because they're both so small that, yes. Again, when you have p-values below 0.001 in studies, they don't even record the value. Like now here, they would just say we found a p-value below 0.001, for example, at their discretion. Here, I was just trying to get a better idea of diagnosis by chest pain, by grouping the data frame by level of chest pain, basically, and looking at the diagnostic levels. And here we conclude that the relationship between chest pain and diagnostic category holds for both levels of the gender variable, and therefore it's not a moderated variable here. Something else is that in case we had found that gender is a moderated variable, we would still not be able to imply causation. We would just get a bit closer to the truth, to the true causation, but we would certainly not be able to imply causation here either. Yes?
Can you also run a multivariate regression analysis with this second variable and see if the significance improves? And then from that conclude that this is a moderated variable?
You'd be able, yes. Yeah, because that would tell you, and that's why when you do multivariate regression, you add the variables one by one, ideally, right? So that you see how they change. Sometimes you add a variable, and then it turns out that another variable that you already had becomes insignificant, for example. That's why you add them one by one, to see how they interact with each other and with the variables you already have in your statistical model. So here I was just putting the note that when two variables are correlated, so when we find a statistically significant relationship, it's possible that X causes Y, or Y causes X, or Z causes both X and Y, basically. And it's also possible that they're correlated by chance, which is what we call a spurious correlation. Here I was looking at age and cholesterol. So I drew the direct plot. We spoke about this before. We see that the regression line slightly descends by age, actually. And then Here's an explanation of the R coefficient. So when you have a quantitative explanatory variable and quantitative response variable, perhaps that's where the R coefficient, this is the test that's easiest and most familiar to everyone. It's a statistic that can go between -1 and 1. It measures association, not causation, as all of them. And then it's a number that tells you how strong your correlation is between the two variables, and if it is, basically. So let's check it here. Print association between age and cholesterol, right? That's what we said we're looking at. And then we take the SciPy stats Pearson R statistic. So this is what we most frequently refer to as R, as a correlation coefficient. So we give it df clean copy age and df clean copy cholesterol. And this is the R the correlation coefficient it found, -0.06. That's what drives the slope slightly down. And then look at the p-value, for example. It's 0.06. So in this case, we say we cannot reject the null hypothesis. So it would appear that age and cholesterol are independent of each other, which is supported by the reg plot. Why it's important to always draw a reg plot with quantitative variables? Yes?
Is there a way to establish causation at all?
You can, it's one of those things that you can only get very close by, but you can never get right there. The only way you can establish causation is it's in a true experiment. So that's why if you go back to the definition of a true experiment, it's something where you control all variables except for one, which you modify yourself, basically. And with observations assigned randomly to the two groups in the experiment. And that's the closest you'll ever get to causation, pretty much. The reason it's always important to draw a reg plot for quantitative variables, I was saying, is that sometimes the correlation coefficient only measures linear association. So sometimes it's possible that you're going to see a very good polynomial association, but your R coefficient is going to tell you the two variables are not associated at all with each other. But when you draw the reg plot, then you find a nice sinusoidal curve, for example, and then you realize that there is a relationship there, but it's just polynomial nonlinear, and the correlation coefficient misses it completely. So it's often advised to always draw reg plots as well. And here we have linear regression, and logistic regression, and these are the last two things I wanted us to see today. Again, I put here a lot of explanations around what are their assumptions. As we said, we always make assumptions. So you have independence, you have linearity, you have normality. You're always making assumptions, basically. And here I said we're going to create a multiple regression model, and we're going to investigate the relationship between our explanatory variables and then our response variable diagnosis. So here you have categorical variables and quantitative variables. I divided them in two, and you'll see just now why. Before you get into multilinear regression, it's a good practice to recode your variables. You need to center your quantitative variables, and then you need to make sure that your categorical variables have a value of 0 at some point in them, basically, so that one of the groups of your categorical variable gets coded as 0. Why this is? This is simply for us for interpretability, basically. Because this is how when you center variables, you're basically holding them constant at 0. You'll see just now in the ANOVA table. So how do we do this? We look at chest pain, for example, and we see that we don't have 0, so we need to recode. I recoded the 1 to 0, the 2 to 1, and so on. And then you use the map function to recode it. Here, fasting, blood sugar, we have a 0 variable already. Rest, ECG, we have a 0, 1, so we're fine. Exercise angina, we have 0 already. And now we move to the quantitative variables, which we need to center. And the way you center quantitative variables is that you take your series and you subtract the mean of the series from every value. That's what's going to center it, basically. So in total, what this means is that your series is going to have a mean of 0. Then I look at all the columns. We just created quite a few new variables, so I'm listing all of them here. And then I call the new data frame we'll be using df clean copy C for centered. And here we only take the variables that we just centered or that we just recoded for the categorical ones. So we end up with this data frame. We have age-centered, we have gender, we have chest pain, we have rest blood pressure, cholesterol-centered. So all the quantitative variables have a C, they're centered, and the categorical ones have been recoded if needed. And here we start to run the linear regression model. So we look at whether sex is a good predictor of age, for example, in our data set. We find an F statistic of 0.8, very low F statistic, and then we find a probability, so an associated p-value of 0.3, which is way higher than 0.05. So we can reject this relationship. And then this is the approach you take, as we were just saying before right now. So you add one variable at a time, and you see what influence that has on the statistics you just had before. So model 2, we create a new object, and here we try to see whether sex and cholesterol have a statistically significant association with age. What do we find here? We find an R squared of 0.005 only. The R squared, if anyone doesn't know, it's a way of explaining to you how much of the variability in your data is explained by the model you currently have. So here, it's 0.5%, it's almost nothing, basically. So sex and cholesterol don't help us predict age almost at all. Again, we have a non-significant p-value, 0.152. And here we find the individual coefficients. And again, you see that they're not significant based on their p-value here. But at the same time, their confidence interval includes 0, as we said. And here I created a full model, right? Model 3, SMF, OLS, formula, age. And let's use all the variables we have to help us predict age. And then we signify when they're categorical. So chest pain is categorical. Rest ECG is categorical. And then let's fit the model here. And let's look at the summary statistics. So here we have an R squared that moved up to 0.278, right? So we explain almost 30% of the variability in age with the variables we just included in our model, so from our data set. And we have this time an F statistic of 21 and a p-value that is very significant at 1.25, E minus 43 basically. So again, you add 42 zeros to the left. So you're way below 0.05. And the table gives us the associated coefficients for every level of our categorical variables and for every quantitative variable as well. And this is how you build your model. Y equals, this whole model, basically the intercept plus each value that you find here for coefficients multiplied by the number of those observations. Let's look at the p-values here. So we see that the first group of chest pain has an insignificant p-value. We see that the second one does the same, the third one as well. So here, these are already three variables that we can exclude from our data set, basically. They don't help us predict age, actually. Here, for this variable, the coefficient is not meaningful. And here, I was saying that, okay, so we managed to explain 30% of the variability in age, right? But let's run some diagnostics now. And these are diagnostics you can always run for linear regression. Let's run a QQ plot for normality, for example. So we create a fig1, and then from StatsModels, we use the QQ plot function, and then we look at the residuals. So what you find here is that the residuals of our model are actually very close to the red line, which is the ideal line. So that's if your residuals are normally distributed, which is one of the assumptions we're making when using these models, your blue dots, which are your actual residuals, are going to follow the red line very closely. And here you see that they do. So we don't have problems of, we don't need to suspect that the relationship is actually highly nonlinear or something like that. Then I draw the residuals here. So these are the Pearson residuals. And what this allows you to do is that it standardizes all your residuals, so allows you to see how they're distributed. And what you'd love is for them to be as close to the 0 line as possible, which means that they're very small. Here, you see that you have quite a few between 2 and 3 standard deviations. That's what the y-axis shows you. And you have quite a few, actually, well, you have a couple that are above 3 as well. So the problem here is what this tells us is that our model is not very good at explaining the variability in our response variable, which is what we knew from the R squared as well. We can only explain 30%, and that's what you see in the residuals as well. And a last diagnostic that you can apply to linear regression is the leverage plot. And what the leverage plot allows you to see if there's any points in your data set that significantly modify your model, basically. So here we'd have to go to point number 33, index 33, and figure out, it's a high leverage point, and it also falls close to 2 standard deviations away from our mean, basically. So this is a point that we have to investigate because it significantly impacts our model. Sometimes you find a lot of points like this, and you need to go look for each of them, basically. Yeah?
What is leverage again?
Leverage, that's a measure of how important that one point is in your model, basically, how much it modifies your model. So like what you look at this graph is how far away from 0 the residuals are, and then leverage tells you how important they are, what impact they have in your model, basically. So because if they're far away from the mean, but then they don't have an impact on your model for one reason or another, you don't need to worry about them so much. But if they're both far away from 0, and then they have a high impact on your model, leverage means impact here, then you need to investigate them because they significantly impact the results of your model. It's a way of looking for residuals, basically, and trying to, you take the problem the other way around. You look at the residuals of your linear regression model, and then you try to figure out what causes those standard errors, basically, those residuals to be so high. Yes?
What should you do with that?
You need to go look at that observation and try to figure out whether it was misrecorded, for example, whether there's a good reason for it to be there. It's basically something that tells you go to your data set and then look for this specific point. Yes, decide if it makes sense to keep it or not, basically, because it significantly impacts your model in any case. And here, we're getting close to the end. I wanted us to finally go to our actual response variable, which is a diagnosis binary as we coded it. And because we have a categorical response variable, we don't use the linear regression model, right? We use a logistic regression model here. And here we use the SMF logit model. So the formula, we give it diagnosis binary as a variable of chest pain, basically. And it's very similar to the way you'd analyze it for linear regression. Let me see where we have the full model. Yeah, so this is the analysis of the full model, basically, for the diagnostic binary variable, response variable. So here we have all the variables we gave it. You see that you have several whenever it's categorical. And then you have the associated coefficients, the p-values, like before, and then the confidence intervals, like before as well, basically. What you do find, however, is that for logistic regression, it makes more sense to talk about odds ratios than about coefficients. So rather than look at the coefficients in the previous table, we calculate the odds ratios here. So NPX, LREG, 3, and we take the params, basically. And whenever an odds ratio is higher than 1, you can say, basically, that, for example, here, for the categorical sex variable, if you're looking at the first group, so at a woman, you'd have a 3.7 times more chances of having a diagnostic binary value of 1, basically, so having a heart pathology, assuming you hold all the other variables constant. And you read like this, each explanatory variable in your logistic regression model through the odds ratio. So it tells you how much more likely you are to fall in the level 1 of your response variable, assuming you hold all the other things constant in your model. Here we calculate the confidence intervals, and I see we're way past, but I wanted to tell you there's quite a bit more here, and it's done on purpose. We weren't meant to go through all of it, but again, it's something that I wanted people to be able to take with them and to play around with it and to consider it, tinker it, adjust it, improve it as a blueprint of how you start to look at the data set. I'm using decision trees and random forests a bit later in this notebook to look more at the model and to try to come up with a better predictive model, basically with a higher accuracy, and also to look at features that I would actually keep in the end as part of the feature engineering part of the process. So the notebook doesn't end here. It's all public. Please don't hesitate to use it, and please email me if you have any questions, if you want to discuss something, if you want to work on it, or if there's anything I can assist you with. Thank you all for your time, and I'm around. Oh, thank you very much.